Thank you very much. We were having just one presentation on eye tracking. This sounds like this is something similar eye tracking, but I have to warn you that this is very different eye tracking we are doing. We have eye trackers that people are wearing on them. They have these goggles on them, and that allows that we can use them in real classrooms. So whereas Dimitri presented a study where they did 24 experiments for 40 students, we have not experiments but lessons that last 45 minutes or 75 minutes depending on the school that we were in. So our data is in that sense very different. Also, because of that, our number of subjects is smaller. And this is a kind of methodology that has been available fairly recently. These wearable eye trackers have not been around for long. And when they came first, they were very expensive and few researchers have had opportunity to purchase these. So we are in the stage where we are still developing the methodology and learning what to do with it. So I would like to compare this for the time when dynamic geometry systems came. There was kind of this excitement and there's so much wonderful we can do with it, but we don't yet quite know what that is. So I'm feeling that with mobile eye tracking in real classrooms, we are very much in that situation that it shows a lot of potential, but we're still in the stage that we don't really know quite how we should be doing it. So there's lots of things we are working with, very basic questions. I want to highlight here my co-authors, Miika Tойванен, who just left our project to a startup company, so he's professionally developing this stuff more. He's the guy who is behind the gaze trackers that we're using. He was in the team developing them, and he was actually building them for our project as his first task when he started in this project. Took him 2 weeks to make this. 6 sets of eye trackers. And there's Энрике Garsиа Mорeno-Эстева, who is been with me from the early pilot stages of this eye tracking, and he's actually there behind the camera, part of the data collection process. So they are not here, unfortunately. We have also a team of other researchers in the project there who are not directly contributing to this paper, but are in the team of eye tracking that we do. So Anu Laine, Eeva Haata, Visayani Salonen, and Jessica Salminen Saari, they are also part of our research team. I'm going to talk now about using research for multiple person eye tracking. So that's one of the extensions we do from laboratory-based tradition. We're looking at how people collaborate and how their visual attention is behaving when they work together as a group. That's a big stretch from how eye tracking has been used. So there's much research in eye tracking on focus on more simple cognitive processes, especially in reading, which is the kind of the fundamental basis for eye tracking studies, how reading is done. And there's lots of kind of very low-level cognitive processing, and there's much research on that, also some in mathematics, but not so much as in reading. And the kind of more complex tasks have only been emerging more recently. There's been a kind of very strong tradition of experimental research with very well-controlled stimulus and timed stimulus, which leads to very narrow tasks. Like the kind of research they do on problem solving on insight tasks are typically very different from what we do in math education. When they talk about problem solving with eye tracking, they have a kind of something visual that is then, aha, now I got it. And that's the problem solving process. And that's very different what we see as kind of the interesting part of mathematics education in problem solving. The several steps that you move towards the solution, you get insight from other students in the classroom. So we hope to get some understanding about these processes within our general project. So for this presentation, the goal is a lot more modest. So we're looking at two conditions. We had some classes working with paper and pencil, and some classes working with GeoGebra. They had the same task that we had chosen in a way that is not trivial. It makes them struggle enough that we get some interesting problem-solving behavior, and that it's reasonably similar to solve with GeoGebra and pen and paper. So we couldn't really use the essential aspects of dynamic geometry, tracking and those as the part of the problem. So they can use it as part of their solution, and some did, but that's kind of not essential in the problem to have this kind of feature to be able to solve it efficiently. We use here as a background some research by Glöckner and Herbert, who kind of synthesized their findings and like in the literature that short fixations that are less than 250 milliseconds are typically related to more automatic processes. And long fixation, and they put the borderline at 500 milliseconds, are typically related to more elaborate processes. There's also some research about cognitive load, how cognitively challenging something is. That also indicates there's very solid research about the longer fixations are related to cognitively more demanding tasks and shorter fixations to cognitively less demanding. But these borderlines, 250 and 500, are just kind of, I would say, more like rule of thumb than a fixed thing. The kind of hardware we use, so Mika has been developing these in their project. So they see the eye tracker goggles, so they don't have glasses here, but they have a camera looking forward, two cameras looking at the student eye, and there are small infrared LEDs that have lights that are reflected on the cornea, and that's what's used for computing the gaze direction. So the data is recorded in a laptop that they carry in a backpack. So that's kind of a little bit encumbrance, but they are able to move in the classroom. And they do that, they go to the board, present their solution. That's not part of my analysis here effectively, but they have that opportunity. And they do use it at some part of the lesson. And the fun thing here is that it's based on the open publishing ideology that these glasses are, the instructions are published. So it's 3D printed frame, and the components you can order online from different providers, and then you can basically make them yourself. It's not a trivial thing, and it's not a polished product, but in principle it's something that you could do in your own laboratory, that you hire an engineer and you do this thing. And it's the performance level is like they did in the paper. Compared with the commercial alternatives, the performance is on the same level. Actually, it's better than SMI, that is very sensitive to glasses being moved, but this is robust against that. The students can take glasses off and put back on, and it's still calibrated to the equal level. That was actually one benefit of this system, that we calibrated them once and we collected data from 2 lessons. So we didn't have to recalibrate for the second lesson. Okay, so the software, how it does it. So first there's the camera looking at the student eye, recognizing fixation. So when the eye is not moving, it's a fixation. That's simple as that. And then it combined the information about the eye position or the direction of the eyeball to the information about from the scene camera, and it produced a red mark on the screen. That's the place where the student was looking. And it's about 1.5 degrees accuracy, so you could say that it's about this much accuracy. So the actual fixation is somewhere around here. It's slightly weaker at the edges of the screen and more accurate in the center of the screen, but that's kind of the rough story about that. We also have placed these visual markers in the class. Sorry, it's not easy to navigate it. So this kind of QR code looking things. The software recognizes the closest one. In this case, that's the closest one, and computes. I'll show that in the later, and it's in the publication as well, that how it computes the location. It makes an affine transformation so that it's all these are kind of placed on each other, and then you can compute how it's like that. That visual marker then defines the coordinates of and that is used to compute what's the location, and we can then even produce heat maps. So gazes in relation to the same visual marker, how they can be summarized as a heat map. Okay. So our research design overall for the total study, we had 4 classes, 2 with paper, 2 with GeoGebra. In each class there was teacher and 4 students wearing these gaze tracking glasses. They worked collaboratively on a mathematical problem, and that time in different classes was from 32 to 56 minutes, so slightly more challenging problems than Dimitri was using in your study. And we had the same task across groups, and we had the same structure, and we scripted the teacher behavior. So that was our way of reducing the variability, so that each class would have roughly the same structure that would allow us to summarize things. So there's think alone, work with a friend, 2 pairs collaborate, and then it's discussed within the whole class. So this is a structure. And the teacher's role, we scripted that they would be not providing hints how to move forward directly. They would be providing encouragement, emotional support, and they would pose questions that elicit students' answers that clarify their thinking. So that was, there's special reason, but I'm not going to go into those details. We did a preliminary analysis to see if there are some individual patterns of students that some might be having like different way of visual behavior than some others, and might not be making a fair comparison. So we chose 8 students that we saw as comparable. So we ruled out, there was 1 with technical difficulties, and then 3 that we ruled out because they were standing out as having very different gaze behavior during those phases of teaching that were not relevant for the tool. Those phases when teacher was explaining the task, or when the students were presenting the solutions on the board, those should not be depending highly on the tool, whether it's paper or GeoGebra. So we thought that that's a place to look at the similarity of different students. So we looked at with 2 different statistics. We used the Mann-Whitney, I'll use this one, there. Mann-Whitney and Kolmogorov-Smirnov. And Kolmogorov-Smirnov is more sensitive to differences in distribution shape. And we see the results that in the tool independence, so that should be not affected by the paper and pencil or GeoGebra condition. We see that the difference between these 2 conditions is not statistically significant, even in the Kolmogorov-Smirnov. There's slight indication that there might be some individual differences, but they are not very large. And when we look at the tool-dependent phases, we see much clearer difference between the GeoGebra condition and the paper condition. So this suggests that overall, there's some difference about the fixation durations between these 2 conditions. We looked at more specifically where the difference is. We divided the whole data into deciles of fixation. So we had the 10% of shortest fixations of the whole data, and that defined as the threshold. 103 is the longest. The technical shortest fixation we could catch was 80 because of the frame rate that we have. So we divided the whole data into segments of 10% of the whole data. So the expectation should be here that everything is 10% if it's according to the average. And here we see that there are some quite clear differences between those 2 conditions with GeoGebra and with paper and pencil, especially for the longest fixations, which in this case is 1 second or longer. There's much more long fixations in the GeoGebra condition. We see also some difference in the mid-range, that they are more common fixations in like they are more frequent in the condition of paper. And then of the quite fairly short fixations, there's again over representation by the GeoGebra condition. So there seems to be, in GeoGebra condition, both long fixations related to very elaborate processing and short fixations related to automatic processing, more frequent than in the paper condition. We looked at specifically the longest fixation, and this is, I think, the coolest pictures in my paper methodologically, that we used these visual markers to define a coordinate system, and all those fixations that were identified in relation to this visual marker were then summarized in a heat map. So there are two students' heat maps, both on their own computer screen, and we see certain areas that they focus on. It summarizes the kind of the background picture, because it's also changing over the lesson, the background picture. So it's providing a summary image, and there's some inaccuracy that is not sharp picture, but we can go back to the original video and see what's the thing there. You might recognize that it's GeoGebra menu bar up here. So that's where the menu bar starts. Both students have lots of fixation in that area. And the other area here is where they had drawn their own solution. So they both have fixations on the menu and then on the solution they're working on. The really interesting part was when I went back to look at the original videos. So the long fixations seemed to be located in the same way. But looking at the video, they were very different behavior. So for one student, it was that the student was carefully operating the mouse. Oops, sorry, I wasn't supposed to do that. Carefully operating the mouse to get the point in a solution to exactly the right place. That was behind many of these long fixations. And the other student, there was a number of long fixations where he was not manipulating anything on the screen, was just staring at the picture. And then after some time, he drew a better solution for the same problem. So clearly, one was manipulation with the tool, the other one was thinking about the problem and just working on the edge of the solution and staring at the image. I have one more picture here that I want to share. That's when we use the visual marker that is attached to the forehead of a student. So the student is moving, so the coordinate system is moving, and people around or the environment is also changed. So we see here student having fixation here on a person, and actually this is the same person, the teacher, in two different times. So it's combination of different time moments. It's kind of funny, this kind of ghost image, but it allows quite fast coding of the target. So I could recognize from this, knowing the overall structure of the lesson, okay, that's the student opposite to this student, and the teacher behind the student is there. So I could recognize, okay, these certain fixations are fixations on teacher without having to code them one fixation at a time in the original data. So that's kind of that's a methodological advice. I don't know how many of you are able to appreciate, but that's huge help for us. Coding 1 minute of gaze tracking data with our original approach took almost 2 hours on average. And this is going to speed it, very much. I'm really glad that we got this solution to our data analysis. But yeah, we see there this social gazes on the face of the peer and face of the teacher. So what we can conclude this. So this, primarily I'm here because I think this is cool methodology and it has lots of promise. But maybe I can deliver already something. So yes, there is quite clear distinction between the fixations in these two conditions. That it seems that working with GeoGebra has some influence on the average number of fixations. There are more short fixations, fewer mid-duration fixations, and more long fixations. So it requires to go into more detail to get really confident answers about that. But it clearly shows that this is a measure that tells something about when we go into the class and collect this kind of gaze tracking data, the fixation durations distribution tells something about how the lesson is going on, what kind of thinking and actions are there. We were very happy that the visual markers worked so well that we were able to code 89% of the long fixations. 89, yeah, of the long fixations. And we can use these to produce heat maps, which is, I think, a nice way of summarizing data. So that's kind of methodological advance that I'm really proud of our team about. So it seems like we have a method to summarize in a reasonable way data from real classrooms with eye trackers. So looking forward to your questions and comments, and thank you for your visual attention. This is part of our team. Not quite everyone was during that event, but. And you can follow us on our website, so it's there. You can.
So, any questions?
Send me an email and we'll send you the link.
With eye tracking, it's fascinating. Eye tracking is really fascinating. I think a really interesting tool. But I always have the question, what does it say? So is it possible that the computer physiologically grasps some kinds of, it does not, because there is a kind of difference. And so I always ask myself, what does it mean when the eyes are looking for a long fixation at a specific point? I could look at you, but don't see you and think of anything else.
I think that's with almost all our methodologies. So, you know, a student is making gestures. What do these gestures mean? Yeah. Or even if a student is saying something in an interview, we still have some level of interpretation of what does that student actually mean when he's saying like that.
But how do you grasp the meaning? So that's the point, I think.
Yeah. So we do combine this with other data. So we are triangulating. So we do use post-lesson interviews, and we use kind of outside. We interpret the things we see in the sequence of the lesson. So we see things contributing. So something that I'm going to present next summer at PME, I don't think too many of you are going to hear my presentation there, so I can share something. There's quite a nice example of these students working together, and I can see in the data that they notice something that another student has drawn in their notebook. And they, in some cases, they draw it for themselves, or they gesture the same shape as a potential solution. So we can track how the ideas are traveling in the group from one person to another in a new way. So, and in one of our studies, we have really also interesting kind of showing how detailed it is. Like this, student solutions are this close to each other on a notebook, but with eye tracking we can see that when they are looking at the student's notebook about the solution, a different solution, we can check that only one of the other three students is looking at that solution. The others are looking at the other solution. So we can do this kind of quite detailed analysis, what they are focusing on when the environment is natural, which typically includes multiple potential targets for attention. In laboratory settings, you control the targets. In real life classroom, you can't control the targets so well, so you have to have a method to identify them in another way.
Fascinating. I enjoyed it. Since I know little about eye tracking, does blinking play any role in understanding or grasping or picturing? And the second question comes whether the tool that you use can record blinking. And
yes.
All right. So
we do have blinking. Well, technically, we don't recognize blinking, but we assume, well, we have the video of the eye, and we could look blinking, but currently the software only computes when the pupil is not visible in the eye and code all of these into blinking. It can be also a look very sideways or some other reason that the eye is not visible. Those are coded as blinks. So I think blinks are important part of information. It's one that we have not analyzed in context to our project, but I think that's definitely one thing that you could look into. So there's this fixation durations, there's blinks, and there's also the saccade length. So how volatile the saccades are from one fixation to other. Are they more focused with short transitions, or are they long transitions? So these are things that don't require recognition of the targets, coding of the target, which is the labor-intensive part. So these are things that could be done automatically. So definitely that's within our plans in future to also include blinks in the analysis.
Thank you very much for the presentation. My question to you is this eye tracking tool, how it could help students with physically challenged. For example, they can see, but they can't speak.
Right, so
that's my first question, yeah.
So if I answer the first question first, so it requires, we have chosen students with normal eye vision.
Yeah.
There's been some people have been trying, and we also tested our system with, it seems that it works well with contact lenses, but we haven't gone there just to be sure that we have a good quality data. It's problematic if you don't have a normal eye vision, in the sense that your other eye, I don't know, it's lazy eye in English. There's more technical term for that. Okay, apiopia. Yeah, but that would be a problem for the method. And then in principle, you could use glasses with them if they fit physically, but not all frames fit physically with these, but they become an obstruction. So we also didn't include anyone with glasses. And a funny thing with our software is that it recognizes the pupil as a dark spot. And if a student has mascara on, it makes false recognition. So we have to ask our participants not to wear mascara during the recording. So that's a barrier for some students.
Yeah. And do I have time for the second question?
Yeah.
The next question is...
oh, sorry. You mentioned the deaf people. And
yes,
I think
yes.
that this might be a good way to get into, if people are having other disabilities, but they have a normal vision, this could be a way of getting better understanding of their thinking.
Yeah.
So, sorry.
Second one, you have just shown an example with the dynamic geometry, GeoGebra. And have you ever tried with this eye tracking experiment with the multi-touch technology?
No, we didn't have that in any of settings. There's tablets being used, so touchpads. So
tablets and also active dish. In our university, we have this active table.
Yeah. So that's where we have been. So that's one of the things that I find very promising to go into with eye tracking. There's also these vertical surfaces that, if you know Peter Liljedahl's work of building thinking classrooms, I think that would be nice to study that with eye tracking. But we limited our situations in a way that it's not too much variation. So we focused on primarily collaboration around the table, so it's similarity across the situations.
Thank you.
I have two questions. One is super technical about calculation of a distance from a marker, and I guess that's also Miho is interested in it, so I will ask it in the outside. And another one is, I think
basically it's just very simple that you use the information of this and you kind of just make an affine transformation, so it as if it was looked from the direction.
But in order to make a affine transformation, you need to know the surface, so you need more than one marker, it seems to me.
No, because
How can you know how to transform a surface if you know only one point from the surface?
you know it's a square.
So you recognize pieces of the square. Okay,
Yeah.
that makes sense. Yeah,
yeah.
thanks. Yeah, that's what the question. So you recognize not the position of marker, but pieces of marker.
You recognize the image on the marker, so you have the full marker as the information. You match that the marker images are completely,
okay,
and you.
thanks. Yeah,
I think it was
this-
affine transformation in the software for that.
Yeah, thanks.
And then you
This
use the same
makes-
transformation. I think it gets some error if there are things that are further back and closer in respect to the marker. So that's a kind of compromise
Yeah,
that we
but
do.
this will be always so with all equipment for sure. Yeah, thanks. That makes full sense. And another question is concerning exactly results. There's a large amount of long fixations into conditions, and you told that the long fixations with GeoGebra are of two types. And I wonder if you have analyzed long fixations with not GeoGebra, and if you
No.
can say that these additional fixations are due to one of those types.
That's one of the things we have to decide, that where we put our time next and what are we going to analyze in the next stage of looking into this data. Because that's going to require manual work. Somebody's looking actually what they're. So I chose the longest because that's reasonable amount. And then I used the heat maps to use it. So that's we are going to go somewhere with that, but we haven't yet decided what we do next, but it's still requires quite a lot of work to do that analysis.
Because I think that if we see that in GeoGebra, long fixations almost always, additional fixations almost always belong to the choose of instrument or trying to put, that would give us very clear practical application of the result. Yeah, that's what I wanted to stress.
Professor Hannula, as all know, eyes are the mirror of the tsubu. Is there essential difference between the state of pupil souls using GeoGebra and pupil souls using traditional paper and pencil? Thank you.
Well, based on our results, I'm inclined to say that probably there is. But I'm not very confident on that. So the number of students we analyzed and the level of analysis is not that deep that I would have high confidence. But it seems that there seems to be a quite clear difference between these two conditions that stays across. So we're going to get some more students into this analysis and looking at some of the other fixation durations to be more detailed. But it seems that there is, yeah.
For example, the right end.
Yeah. So it could be something as simple as fatigue. So for some reason, people working with computer screen, that their eyes get more tired and therefore there could be more long gazes. So it could be something as simple as that. So I'm not yet highly certain that it's because of the tool. But I have to say that when the research on reading is much more advanced in that, and they really found that people reading the same text on different media, paper, technology, and different types of technology, it influences the fixation duration distribution. So reading the same text from two different reading softwares or reading devices, electronic reading devices, the gazes are influenced by. So the soul is influenced by the kind of technology that you put your money in. So depending which devil you deal with, you have a different soul.
And I can add that it depends how familiar you are with different kinds of things, then different things happen. I just share a short experience and then I go a bit more to the epistemological aspect. So I never am able to find my own mistakes on the computer, but I'm able to find my own mistakes on the paper. And so, yeah, it depends probably on people and the age and what they have according to different kinds of impairments. What I like here is that is a really new tool and instrument. We never had this before. And Maike Schindler and
Joachim Lilienthal.
yes, they have written a nice paper about the necessity of getting theories that allow us locally or at specific point to make sense of it. And I really would appreciate this work, because we all use tools, many people use tools without, thinking of this kind of restrictions and limitations every tool and instrument has. And so that's really something that could bring us a real step forward, because we never did this in our community, and therefore I appreciate that really. And I would like to know whether you have a structure or a conception of how to investigate an instrument according to our own purposes in our community, because the physicists they have things like that, and that's something that reminds me of that.
Can you clarify when you said, do I have plans to research the instrument?
Yes, so to find out what the instrument does, what it does not do,
And you talk about the eye tracker?
Yes, according to the eye tracking, you can use one at a time, you can use two at a time, and so this is one glimpse to go into that one. But I would like to know, is there a kind of plan of going somewhere, finding the limitations of such an instrument? Because when you do high energy physics, you have to have it, because the experiment can only do once. It is costly, I know, 100 whatever billion, or I don't know, euros or dollars. Yeah.
So I wouldn't compare this research to high energy physics, but I feel very much like an explorer
Yes.
who's just found a new continent and started exploring the coastline. Yeah. And I see lots of potential there and lots of kind of fascinating things, but I have no idea how broad the continent is. And
so the conception is an aim. So you cannot start with a conception. It is an aim to have a conception how to describe the limitation and what it does, the target knowledge according to this kind of tool.
There's two things, like as a research project or research, let's say research field, opening a research field of mobile eye tracking in real classrooms. There's kind of, I don't think I can post a kind of good research agenda yet. But I have lots of, like when we go to more specifics, like when we do a study like this one, I had to have a more clear focus what I'm looking into. I decided to compare these two conditions, GeoGebra paper, that was already in the design, and then looking at the fixation durations and finding ways how I compare how I rule out the odd cases from the sample. And so I had to think through what is the question I can answer with this data and how to make that an explicit one. But as a broader project, it's very much, still stumbling in the dark house and trying to find a light switch.
Okay, we have another questions?
Last question, I think.
There's Jeff as well.
Yeah, I just would like to add to your comment. I happened to watch Maica's paper. She presented her paper on eye tracking. Something connected with this, but the experimental setting seems to be a little bit not very clear, because the students were sitting in a dark room and they were all the time connected to the computer. Is this the case in your experimental setting also?
No, this is in real classroom. So actually we had one lesson where they were just in the normal classroom, and that was primarily for us for ensuring that they are used to the equipment before we do our problem-solving session that we focus on. But it's something we negotiate with the teacher, that they want to use this problem in their class, and it's kind of aligned with Finnish aims of the curriculum to develop problem-solving competencies and collaborative work. So teachers generally were okay with the task if they were okay of us intruding with all the technology, carrying cameras and everything in the classroom. So so as normal lesson as you could possibly have with this kind of technological intrusion. We also did collect actually the students and teacher feedback, how they feel in this lesson compared to the normal lesson. So that's a part of analysis we haven't done that yet. I probably should assign one of my students to look into that if there is some obvious influence of the. It didn't seem very striking, at least what we got the interviews, that they said that, yeah, it's like going to the 3D movies. You know that you have the glasses, but when the movie starts, you forget them. And the same here, when you start working with a problem, you kind of forget that you're wearing these glasses. Not completely, but it doesn't dominate your thinking.
So just last question.
Yeah. So for me, I think this is what you were saying. This is very much of the development of a new kind of method in search of a problem that that is solvable with this kind of method. And so for me, one of the keys would be identifying what kind of problem can be solved with this kind of method. And I was impressed with Angelica's comment that like you, I have a problem that when I'm editing text, I do much better with a hard copy than I do with a screen. So I would think that for that kind of well-delimited problem, eye tracking might provide some kind of insight for what I do when I'm looking at a hard copy and what I do when I'm looking at a screen. And I would imagine there are quite dramatic individual differences in what one's eyes do. Somebody who does well on a screen but not so well on hard copy, vice versa, that there would be real individual differences. So I guess this is sort of an open question. One is that case study analyses, like of individuals, seem like a better unit than homogenizing data. That's one thing. And just your thoughts about how you identify problems that can be seriously addressed with this kind of technology.
So we have kind of, I would say, 3 lines of research in this problem. One is providing case studies that are primarily qualitatively analyzed. And there are some issues that are coming up in there, for example. I won't go into details because of the time. The second one is what I presented here, having these very crude overall measures of things and then trying to see what they tell, kind of the bird eyes view about what's happening in the classroom, and using the kind of data that we have in, for example, here we could use this overall that we look at these long fixations more than half a second and see if there's a difference in under different conditions, how often they appear. So this kind of research could be done in that direction. And the third, I think, most interesting approach is when we coded actually the targets, and then we know something about the situation, and we correlate these. So there's my student is Eva Harta is doing this research on the eye contact between the teacher and students during this kind of scaffolding of student collaborative work, and like looking if the eye contact behavior and who is initiating eye contact is different when the teacher is using socio-emotional scaffolding, or is doing cognitive scaffolding, or is doing metacognitive scaffolding, how these 3 types of scaffolding are related to different eye contact patterns. Or also, like, what are the types of targets that the teacher is focusing on during these different types of scaffolding. So going into that direction is definitely the most interesting one. And I'm really kind of looking forward that we get into the time when we have enough data to look at that before the student gets the aha moment. What can we say about the pattern of targets before that? Because they have some preliminary, like the solutions that are not the optimal one, but they all generate the kind of standard solutions. So how much these different solutions are influencing the time when they get the aha. So kind of before the aha, what happens? So we have the data that can tell more about that process. When a student is searching for a new idea, and we could analyze that, but we haven't yet done that because it requires a bit more work with the coding of the targets and then making sense of that data, but that's definitely within our reach. Oh, I think your boss wants to
Okay.
ask a question from me.
To add just a bit, because for me it's very important discussion. What does eye tracking bring to the field as an instrument? I just want to make a small comment on this, if you're allowed to intervene. That I think that eye tracking, like when we started to be able to videotape what is happening, the first feeling like, oh, now we know everything. When we look at it deeper, we understand that it's just a data source far from data, and we can analyze it in hundreds of ways depending on our research questions. And I think that it's useful, efficient to consider eye tracking in the same way. It's just a coordinate per time. And then we can do with these coordinates huge amount of things depending on theoretical framework, methodology, research questions, and all of it. And I think we're really just at the beginning of developing of very different ways to analyze it. But it's nothing more than just one more coordinate per time, and it's only data source. That's what is eye tracking. Yeah. Thanks.
Thank you. That was
Thank
a
you,
nice
and
way
sorry
of
for intervening here. Just
concluding this.
So, thank you to all and to Markku.